Now, the motion of fluid, which we consider here as a continuum, are governed by the conservation principles. So, as I think has been already discussed on the fluid mechanics lectures. So, the motion of fluids are we can develop based on the conservation of mass, momentum and energy. Now, energy equation based on the conservation principle of energy is decoupled for the incompressible fluid from the mass and momentum. So, we here we will be focusing on incompressible situation. So, we can avoid the discussion on the energy equation. So, for incompressible fluid, we have the equation of continuity that is based on the conservation principle as the divergence of u equal to 0. U is the local fluid velocity vector, it is a vector at any point x, y, z, say if it is in Cartesian. Now, the second equation, which is called the equation of momentum. So, this is based on the conservation of momentum principle. This is basically nothing but the Newton's second law, which is P equal to mf. P is the sum of forces exerted on a fluid element, m is the mass and its acceleration is governed by f. So, if the V is the volume and rho is the density, if I where the volume element we are considering. So, we can write this by this manner, P by V equal to rho f. Now, this can be if I consider a volume element within the fluid. So, there will be a interacting force on the surface of the fluid element, that is the what is referred as the pressure, and also the viscous frictional force. So, this way one can rewrite this equation in this form. The conservation of momentum equation now can be expressed in this way, where this du dt is referred as the material derivative. Now, material derivative, it is not the exactly the total derivative. So, that means here the every element is moving with the fluid itself. So, du dt is in this case we have the form as this is the way we define as a u is a vector. So, u dot grad u. So, this is referred as or this operator way if I write, that is del t plus u dot grad. Okay. So, this gives the operator form. So, the is also one can say the rate of change of momentum. So, the forces surface force and body force. So, the surface force corresponds to the pressure and viscous forces, and the body force corresponds to the body force due to gravity and that electrostatic force as we discussed over here. So, that means the body force can be written as rho g plus rho e e. Now, if I neglect the gravitational force and only stick to the electrostatic force. So, I can express the momentum equation in this form, where P is the pressure, mu is the viscosity, dynamic viscosity of the fluid medium. So, the momentum equation can be expressed in this manner, rho du dt equal to minus del P plus mu del 2 u rho e e. Now, rho e, as we have already obtained from that Gauss law, as that is that Poisson equation for electric potential, rho e is governed by this equation. So, if I substitute here, so I get a situation. Now, I wrote the material derivative in this form, rho del u del t plus this situation here. P is we have denoted as the pressure. So, this is due to the viscous drag or frictional force, viscous frictional force. This is the term which corresponds to the charge density whatever is present. Now, if the fluid is electrically neutral means if rho e is 0 everywhere. So, rho e is the volume charge density of the aqueous medium and epsilon e is the permittivity. Now, if you have a situation where rho e is 0 everywhere within the fluid medium, so this is nothing but the equation of motion of a incompressible Newtonian fluid. Now, another thing is that assumption we have made is that this is a Newtonian fluid, that means there is a linear relation between the stress and strain rate are occurring. So, we now develop the governing equation for the fluid in a aqueous fluid or ionized fluid. So, only extra term which is taking care is governed by here. So, now which shows that this phi and the Poisson equations whatever this equation we have developed are now coupled. So, that means if it is not electrically neutral, so we these equations are depending on each other. Now, we have to know the, as we are just mentioning that because of this movement of the fluids and also the electric field and all. So, if we just go back and have a look over here. So, because of if we have a charged surface. So, due to that there will be a movement of the ions, positive will be attracted to the negative electrodes and negative will be moving to the positive electrodes, and there will be a movement of the ions. So, the concentration of the ions which is creating the charge density will be different within the domain itself, within this domain. So, you have a different concentration of the ions. So, now we need to know the distribution of the ions in order to get this equation correctly, equation 10. Okay. So, that means this equation 10 demands that we should have a expression for the rho e which is governed by the distribution of ions. Okay. Now, in order to do that, we first define some we measure the how we define the measure the rather how we measure the distribution of ion. So, this is the we call the rho I is the mean density of the ith ionic species. We can consider several ionic species are dissolved. Here we are all considering are the miscible ions. So, that means they are dissolved within the liquid. So, there are maybe several components. So, one of any arbitrary component ith component we define as the mean mass density, rho I is the mass density, Ci is the molar concentration. So, the number of moles per volume, and another important things which we require is the mole fraction. So, if the net concentration is governed by this way, summation of this. So, this mole fraction of a particular ionic species is xi is the number of moles of this species per the net amount of mole. So, Ci by C is measured the mole fraction of the ionic species. Now, charge density are governed by this equation, this relation. So, charge density. So, each of these ionic species are creating a charge which is equal to F C x I. So, F C x I is basically the F C I and Z I is the valence, whether it is a positive or negative or the number of valence. So, this summation is the giving the charge density per unit volume of the ionized fluid. So, with that now the Poisson equation for electric field can be expressed by this equation. Okay. Now, if we have a situation where it is electrically neutral, so that means the net charge density will be 0. So, we will have Z I C I or sigma Z I X I are 0. And N I, do you define? N I is the number density. So, that is okay, is governed by this way, same equation, because it is 0, homogeneous. So, that is why we can have the same equation. And the ionic strength of an electrolyte is defined in this manner. So, if it is a see, this is non-zero even if it is a electrically neutral situation, because it is a Z I square. So, the net amount of this is the C I is the molar concentration. So, net amount of mole per of all the ionic species per unit volume is the ionic strength of the electrolyte. Now, we are intended to derive the equation for ion transport. Now, we are talking about the multi-component fluid. So, let a ionic species which has a velocity say u I and density, mass density is governed by rho I, dissolved in a fluid medium whose local velocity is u and density is rho. Now, this mass density is also related, can be related with the molar concentration by this relation, because mole per meter cube. So, by this relation C I is the molar concentration of the ith ionic species. Now, if there is no way to generate the ionic species, that is in absence of any reactions, so by the equation of continuity, it will satisfy the equation of continuity each of these ionic species, where rho I is mass density and u I its velocity. So, in terms of the molar concentration, we can write this equation in this equation 13 form. Okay. Now, this u I may not be equal to the u, because the ionic species may have different velocities, different ionic species may have different velocity other than the local fluid velocity. So, there will be a difference u I minus u. Now, we need to see what are the mechanisms by which we have a difference. Now, if I we know the equation of continuity for the fluid is divergence of u is 0. So, if I apply over here, so we get a relation. Now, I say that the J I is also referred as the molar flux of ions is by this relation. So, the if I apply over here, so the divergence of u is 0. So, this equation 13 can be transformed to this form by virtue of continuity of the fluid, divergence of u is 0. So, you get a relation governed by this way. Okay. Now, J I are due to what are the mechanisms we can, in absence of course, here we have neglected the gravitational force and also the reactions and all. So, the mechanisms for this ionic flux are the molecular diffusion and electromigration. So, now we have to get an expression for J I, the molar flux of ions due to these mechanisms. Now, molecular diffusions that is governed by the well known Fick's law, Fick's first law for that matter. So, Fick's law means if there is a gradient, that means there is a in the space gradient in space of the distribution, that means there is a difference in molecule in difference in the concentration in spatial differences occurring. So, this molecular diffusion flux is proportional to this gradient, and this proportionality is referred as the diffusion coefficient T I. So, this is the flux due to the molecular diffusion. Okay. Here it is negative, because you may have a positive gradient or negative gradient. So, depending on that, the ionic species will move along that direction. So, that is why you have a negative. So, Ti is referred as the mass diffusion coefficients. Now, this is a thing here we have taken Di as a single value for the ith ionic species. Now, it can differ, say if you have between two interacting between two ionic species I and J. So, it can have a dependence of this Di. So, here we avoid that one and we consider that Di is the diffusion coefficients for the ith ionic species. Now, another thing is that when these ions are under electric field, so each ions are carrying a charge. So, they will have a Coulombic attractive force and there will be a movement or ionic flux due to this electric field. So, that is the one we refer as the diffusion or the electromigration. So, if Ci is the molar flux molar concentration of the ith ionic species, so it has a charge density F Zi Ci, F is again the Faraday constant and Ci is the Zi is the valence of that ionic species. So, it will have a force as F Zi Ci into E. So, the due to migration of in an electric field of this, we are considering this is the charged volume charge. So, these ionic species will have a flux due to the presence of an electric field, which is proportional to this net amount of charge. So, this proportionality constant is omega I is called the mobility of the ith ionic species. Mobility is basically is the velocity per unit electric field, that is the way is mobility is defined. So, we have two class of ionic flux generation, one is due to the molecular diffusion, another is due to the electromigration of the ionic species. So, this omega I can be written as di by RT, where R is the universal gas constant and T is the temperature. Okay, di is the diffusion coefficients. With that, we can write the equation what we have already derived, the valence equation or conservation of ionic flux. We can write as this manner. Okay. So, now here considering a linear superposition of the two components. This is the two components as due to the electromigration and the diffusions. So, the charge transport equations now can be written in this manner. So, the total flux of the ions, net flux at any point are governed by this is by the fluid convection, this is the diffusion, molecular diffusion, another is the electromigration. So, if it is a neutral, so this part would have been 0. So, that means, if it is a neutral solvent, any other kind of solvent. So, this last term, that means the molecular electromigration term is neglected. So, that is called, this is the basic, also referred as the mass transport equation. So, this is a equation. So, we can now write the molar flux of the ith ionic species are by this relation CIU. U is the local fluid velocity and this is the molecular diffusion and the electromigration. And if I write in terms of the number density of the ith ionic species, so this is governed by this relation. Now, if I consider, so this relation 15 can be written in this manner. So, if I consider a steady state situation, so if it is a steady state situation, so either of this divergence of this NCI or NI becomes 0. So, this can be expressed of this form. So, divergence of NCI, so that means you have a situation where CI u is a vector, of course, minus di del Ci minus Zi di f by RT, because omega I is f by RT, Ci grad phi equal to 0. Phi, how, which notation? I think it's the notation. So, this is the in a steady situation, this becomes the governing equation for the ionic transport. Omega I we have already defined as di by RT, okay, and E is minus grad phi. So, basically this is the thing we have substituted over here. Now, okay. Now, we need to know, because these ions are moving, so there will be a current density will be developed. So, ions are transporting by the equation as we have just derived. So, because of this movement of the ions, you have a development of current. So, this current can be considered, or you can measure the current density. So, that means the ampere per meter square local current density by this relation. So, the flux and what you have is I equal to the Faraday constant and what of course, you have valence and this all this flux. So, if you have n number of ionic species, so we sum over, if it is a binary, so you have Z plus and minus a monovalent situation. Otherwise, you may have a ZZ electrolyte, you may have arbitrary, but two binary species. And also this can be written as, if I write in terms of number density function. So, this is Z I in N I. Now, we substitute this is the relation is for the NCI. So, if I now substitute here, or also we can say this is the, because E, if I multiply with E. So, basically Ci and Ni are governed by this way. So, Ci is can be written as E Ni. This is number density into E, the elementary charge. So, that gives you the molar concentration. So, this is not the one, FCI. So, if I substitute in the flux of, or number dense number, what the way we can say this is the number density flux corresponding to the number density flux. So, if I substitute in this relation, so the current density is governed by this equation. Now, E, if I write in a grad phi form, so we get a situation here as governed by this way. Now, here I have written E by kBT. Now, this since we have we can note this relation, F is basically E into Na, okay, and also R, the gas constant, that is this is the Boltzmann constant Kb into Na. Na is the Avogadro number and Kb is the Boltzmann constant. Now, we have this situation that we have F equal to E N A. So, what we can write is E by Kb T equal to F by R T. Okay. So, because the charge density, so net charge, so Z I F C I N A is nothing but E Z I N I. Okay. Now, N I we can write as which way E N I. So, in this way we can get an expression as E by Kb T equal to F by R T. Now, that is the thing is been written over here. Now, if the fluid is taken to be electrically neutral, that means the net charge density is 0. So, first term is out, sigma Z I N I is 0. So, which shows that the current density is independent of the fluid motion, because fluid motion is involved only in this term. So, also now when there is no concentration gradient, so what we have the and these two terms if it is dropped. So, that means you have a situation where electrically neutral and also the no concentration gradient are developed. So, in that case the current density can be written as F square R T. So, E now we change N I will be now E N A F C I. So, this F C I will come out. So, this E by Kb T is F by R T. So, this becomes F square by R T grad phi Z I into d I C I, Z I square of course. So, we define the electric conductivity of the medium by this relation, this nu. So, nu is we define as the electric conductivity. So, what we find that this is basically the Ohm's law, I equal to nu minus nu grad phi. So, the electric field is proportional, current density is proportional to the applied electric field, and this is the electric conductivity of the medium is governed by this way. Okay. Now, this N I here are solving the previous equation. Okay. So, this is the Ohm's law we can talk about. Now, if you have a ZZ electrolyte, that is d1 equal to d2. So, one can write nu is governed by that relation can be simplified. C0 is the bulk molar concentration. So, next one we will talk about the other part later.